Escape velocity. This is the velocity that one body must be traveling in order to escape the second. And that's such a good definition, I might write that down right now. So this is the velocity a body actually it's the least, it's got to be going faster than that. So this is the minimum velocity. This is the minimum velocity a body must be moving at. Not the most eloquent sentence. This is the minimum velocity a body must be moving at in order to escape a second body. This is the minimum velocity a body must be moving at in order to escape a second body. Note that I didn't say the escape what of the second body. It is not the, so usually the second body is in this context is a large planet or a sun or something, and the body that we're concerned with, its velocity thereof, is something smaller, an asteroid or a rocket or something, a projectile. Note that you can't, even if let's just say I've got two bodies in the universe, one large and one small, the smaller one can never escape the larger one's gravity, for gravity is, well, at least for what we understand, meant to be infinite, or at least will propagate infinitely at the speed of light. So it's not escaping the gravity of the larger body, it's just ensuring that it never comes back again. And you might think, well, if it could never escape the gravity, how can it never not fall back? Isn't it always going to come back again? Well, no, the gravity, the velocity will still be slowing down, but it'll never stop and effectively become negative, come back again. So this is the minimum velocity a body must be moving at in order to escape a second body. So in the previous lesson, we looked at this idea of mechanical energy. And we said that the energy mechanical is equal to the sum of the kinetic energy plus the potential, gravitational potential energy. Let's call it G. Of course, that is half mv squared, and that's minus because gravitational potential energy is zero at an infinite distance. So it looks like that. So when the mechanical energy is greater than zero, means the body is never coming back again. So when that mechanical energy is greater than or equal to zero, it's never returning. So, i.e. I've got half mv squared minus g big M little m on r. When this thing is greater than or equal to zero, it's not coming back again, i.e. half mv squared. And I can take that to the other side to get a sense of what we have to talk about. So when the kinetic energy is greater than the gravitational potential energy, it has enough kinetic energy to escape the gravity well. So when this is true, this implies, so when this is true, the body is said to be in a hyperbolic orbit. Although, do you still call it an orbit if it's hyperbolic? I'm not sure. I'm uncomfortable with the word orbit. Let's say said to be executing whatever. I think that's fine. So it's said to be in a hyperbolic orbit. And if we even think of our old rectangular hyperbola, we could think of distance going this way, and perhaps this is a measure of velocity, although this is referring specifically to its position. Right? In any case, the concept's the same. That velocity is forever decreasing, but it'll never reach zero. It'll never reach that. The zero itself is an asymptote. So in a hyperbolic orbit, so if I've got my large object here, and I've got a smaller one here, let's say it's coming in on a path like this. It's going this way. Then back to blue for a second. That area there, it's traveling in V. And distance from here to here. Not that the direction matters. Is R. I need the R, which I have. Those M's will cancel. And I'll need the big M of the planet. And the planet itself will need a big M. So I can measure its velocity at any point, or its velocity and R together. I need to do them both at the same time at any point to measure its kinetic energy. And if it's greater than this value here, then I know this must be on either a parabolic arc or a hyperbolic one. Highly unlikely to be a parabola, for that would have to be equals there. And in the ideal world, we don't get parabolas and we don't get circles. All right. So we note that we'll just make a note about the velocity decreasing. We note that the velocity will eventually be decreasing That's rather awkward. That's the velocity. Let's not note. Describe which part of the path we're on. So as the body leaves, understand what it means, as the body leaves, its velocity is forever decreasing. It is forever decreasing, but it never, writing's getting messy, but it never goes to zero. Oops. But it never goes to zero. So as the body leaves, its velocity is forever decreasing, but it never goes to zero. If this is true, it'd be nice to find out what that threshold velocity in fact is for any particular distance. So this is what we call the escape velocity. So let's use another color. It's the key term. The escape velocity is given by, it's when those things are equal. So I end up with, I'm going to squash it on here, half mv squared is equal to g big M little m on r, and the masses cancel. And making v the subject, get v equals the square root of 2, just going to multiply that 2 across, 2 g big M, the little m's gone, then I still got the r on the bottom. That's our little formula for escape velocity. Probably not worth memorizing. What am I looking for? Oh, I need a red box. Pretty simple to work out from scratch. However, lots of students feel comfortable memorizing as many of those as they can. Okay, enough being fussy. So V is root 2 gm on r, where g is the gravitational, or Newton's universal gravitational constant. So the classic example is, well, what if I was throwing an object from the surface of the Earth? How fast would I have to throw it in order for it to never come back again? So, example, throwing an object from the surface of the Earth, a capital E. Now, did I write the word hyperbola or hyperbolic up above? I did. Okay, good. It's important. So throwing an object from the center of the Earth. If it were possible, so I need some constants to be able to do this. M equals of the Earth, mass of the Earth, 5.972 by 10 to the 24. It's big. I need the constant, 6.67. Shall we have an extra digit? 1? No, that's not right. It's not 1. 6.674 by 10 to the minus 11. I'm from the surface of the Earth, so the radius of the Earth is 6 million meters, 6.371 by 10. That's the one that I was thinking of, by 10 to the 6 meters. That's all I'm going to need, isn't it? Yeah. 1, 2, 3 constant. So our escape velocity, let's just make it clear, has got to be greater than, should really put greater than or equal to, 2 times g, which is 6.67 by 10 to the minus 11. Times we need the mass of the Earth, 5.972 by 10 to the 24, all on the radius, 6.371 by 10 to the 6, which comes out to be 1.119 by 10 to the 4 meters per second. And I've used 4 significant figures right the way through. 6.674. It's close to this. It's 1.19 by 10 to the 4 meters per second. I'm pretty sure I can claim that that is to 4 significant figures. And just to get that into some kind of perspective, that's about 11 kilometers per second. So you would have to throw something, flick it from the surface of the Earth at about 11 kilometers per second, or faster than 11 kilometers per second, to ensure that it never came back again. If the Earth was the only thing in the universe, well, the Earth and the thing that you're throwing away from it, 11 kilometers per second. So there we go. That does it for today's lesson. I'm Keith Johnston. Thanks for watching.